today we're going to learn a couple more important rules about how to take derivatives. And then once we have those, we are going to apply those to actually solve some motion problems, which is what Isaac Newton developed calculus for in the first place. So, just as an example, suppose you have the function f of x is equal to x squared plus sine of x plus 7. Okay, I'm not sure exactly what that would look like. We could figure it out, but that's not a big deal. Anyway, let's find out what the derivative is. The derivative, of course, never forget, is the function that tells us what the slope of this is going to be at any point. And it's pretty straightforward. You just take each one of these separately and take the derivative. So we know the derivative of x squared is 2x. We know the derivative of sine of x is cosine of x. And 7, that's just a constant. The function 7 looks like this. The slope of that is 0 at every point. So if you want to put plus 0, you'd be all set. So there's that one. How about this one? What if you have f of x is equal to 5 times x squared? What would the derivative of it be? Well, I could have done this with the first problem already, but it's a little easier to do it with this one. Here's the function x squared like this, and 5x squared, recall, that's just 5 times as high everywhere along there. So it looks like this. And so there's x squared, there's 5x squared. So since this at every point is 5 times as high as this, basically at every point you have to be going up 5 times as fast. So basically the derivative of this is going to be 5 times as great as the derivative of this at every point. So it amounts to just this. F prime of x is 5 times the derivative of x squared, which of course is 2x, so that's just 10x. Which means, in practical terms, you take the derivative by just bringing this down and multiplying it by the number in front. So let's try one more, and then we'll apply this to some motion problems. How about f of x is equal to negative 7x cubed plus 3 over x to the 4th plus 7 times, I've already used 7, let's make it 8, times the square root of x plus pi over the cube root of x. How's that for a nasty looking function? Okay? So here's what I'm going to do. Oh, let's throw in a cosine as well. Plus cosine of x plus e to the x. Plus e to the x. There's an ambitious function. What's the derivative of it going to be? So before we start, let's rewrite it like this. This is 3 times x to the negative 4. This is 8 times x to the 1/2 power. This is pi times x to the 1/3 power, and then it's down below, so it's going to be negative 1/3. And then you still have a cosine of x, and you still have an e to the x. Okay? So what's the derivative? In fact, let's make this 6 e to the x. There we go. So what's the derivative? Well, you bring this down. So it's going to be negative 21x squared. You subtract 1. You bring this down. It's going to be minus 12x to the minus 5. You subtract 1. 8 times 1/2 is going to be 4 times x to the minus 1/2 after you subtract 1. It's going to be minus 1/3 pi, so minus pi over 3 times x to the minus 4/3 after you subtract 1. Remember what the derivative of cosine is? It's negative sine, so it's going to be negative sine times 2, so it's going to be minus 2 times the sine of x. And then the derivative of e to the x is e to the x, so that's just going to be e to the x times 6 which is going to be just 6 e to the x again. There you go. So look at there. Look at the kinds of things we can already do. So that's how that works. Let's just try one more just for practice. G of x is equal to 7 ln of x plus 10 sine of x. And so its derivative is going to be, what's the derivative of ln is 1 over x. So, let's throw in a 12 here. So it's going to be 7 divided by x, because the derivative of ln of x is 1 over x. This is going to be plus 10 cosine of x. And then, of course, the derivative of 12, that's a constant, is going to be 0. So there you go. Okay, good. So now let's use that to solve some problems. It's been determined from experimentation by people like Isaac Newton and others that if you are on top of a building which has, say, height of h naught, I'll let h with a little sub-zero stand for the height of the building, and here's the ground right here, and you throw something up in the air with initial velocity of v naught, okay, then, of course, what's this thing going to do? It's going to go up, it's going to come down, and it's going to finally hit the ground. And it turns out that the height of this object at any point is given by negative 16 t squared plus v naught t plus h naught. So this is the initial velocity, and this is the initial height, and this is due to the acceleration of gravity. And so if you didn't have it, if you just dropped something and you wanted to know how far it was going to go, this is assuming no air resistance. So this is like a heavy object, really heavy with minimal air resistance. All you had to do would be to count 1001, 1002, 1003. 1003 squared is 9. 9 times 16 is 144. So if it hit the pavement below or the lake below after 3 seconds, it'd be roughly 144 feet up. But anyway, if you have a velocity and initial height, then it's this. So that's that. So suppose we're on top of a building which is, say, 80 feet high. Say this is 80 feet high, and say you throw it up with a velocity of 64 feet per second. Okay, this is all in units of feet, by the way. Okay, so then let's analyze this problem. By definition, the rate at which the position changes is defined to be the velocity. The velocity of an object is the rate at which its position changes. So v of t, standing for the velocity, is equal to the derivative of the height. And notice I'm using h prime for the derivative. Notice the variable in this case is t rather than x, but that's okay. It's just another variable. And so now let's go ahead and find the derivative of this thing. So we just did something like this. So you're going to bring the 2 down. It's going to be negative 32t. Oh, I'm sorry. And this should have been what? I just changed it to 64 and changed this to 80. Okay, so it's 80 feet up, and the initial velocity is that. So negative 32t plus 64. So that gives us the velocity at any point right there. And as long as we're at it, let's talk about how the velocity changes. The definition for how the velocity changes as a function of time is the acceleration. The acceleration is defined to be the rate at which the velocity changes. So I can write here a of t for acceleration is equal to v prime of t. You got to be careful when you write v prime that the prime doesn't look like it's part of the v. And the derivative of the velocity is just going to be the second derivative of h. So that's going to be h prime of t. Oh, I'm sorry, h double prime of t. That's when you take the second derivative. And what's the second derivative of this? Here's your variable. So you bring the 1 down. This is like t to the first power. You bring the 1 down, it's going to be negative 32. T to the 0 power. T to the 0 power is just 1. And then the derivative of 64 is 0. So this is the height. This is the velocity. And this is the acceleration at time t. Notice the acceleration is constant. It's always negative 32 feet per second squared of the units. So once you have these, you can answer all sorts of questions. Let's put some down and answer them. So let's say find the height at t equals 1. Okay, let's just go ahead and do it. At t equals 1, you'd put 1 in here for height. You'd get negative 16 plus 64, which is 48, and then plus 80, which is 128. So h of 1 is equal to 128 feet. So after 1 second, it had climbed from 80 to 128 feet. Okay, there's that one. How about this one? Find the velocity at t equal 1. Well, here's the velocity. You stick 1 in here, and you're going to get 1 times negative 32 is negative 32 plus 64 is 32. So v of 1 is equal to 32. This would be in feet per second, like so. Okay, if I ask for the acceleration at time 1, it would be just negative 32. I won't even write that one down. Okay? Now, how about this one? When does the, let's say it's a rock, reach the highest point? When does it reach the highest point? Well, let's see. Let's think about it. You're throwing it up. It's going up. It stops momentarily, and then it's on its way down. So the unique thing about the highest point is that the highest point, the velocity, is going to be 0 right there. So all we have to do is set that equal to 0 and go negative 32t plus 64 is equal to 0. And we solve it, and we're going to get 32t is equal to 64, or t is equal to 2. So there is when it reaches the highest point. Here's another question. What is the highest point? Well, we know it reaches the highest point at time equal to 2, so all we have to do is stick 2 in here, and we get h of 2 is equal to what? Stick it in here, you're going to get 4. 4 times 16 is negative 64, and then 2 times 64 is 128. 128 minus 64 is 64. 64 plus 80 is what? 144. So that's the highest it goes. That's the highest it goes. Now, how about this one? How fast is rock traveling, is rock moving, when it hits the ground? And I should be a little more specific. I'm going to say, what's the velocity of the rock? because velocity allows for both positive and negative numbers, where if I just say how fast, then it's just basically saying make it positive. And so I'm going to say, what is the velocity of rock when it hits the ground? Well, okay, how do we figure that one out? Well, we first have to determine when it hits the ground. So I first have to, because this will tell me the velocity at any time, but I don't know when it hits the ground. So I first need to set when will h of t be 0? So h of t is equal to 0 when negative 16 t squared plus 64t plus 80, when that's equal to 0. So luckily, the numbers work out nice here. If you factor out a negative 16, you get a t squared minus 4t minus 5. Well, that's nice. And now this thing factors. I came up with my own numbers, so this would work out very nicely. You're going to get 16 t minus 5 t, oops, I'm sorry, t plus 1. So the 2 times when this thing is going to be 0 is going to be when t is equal to negative 1 or 5. We're assuming that you throw the ball up into the air at time equal to 0. So if we're only looking at positive times, which is when we'll do it in the future, we're going to have time of equal to 5. So that's when it hits the ground. So now we can find out the velocity. The velocity is going to be v of 5, which is negative 32 times 5 plus 64. Let's see, I can do that in my head because 2 of these 32s will cancel this one. You have 3 32s left, which is a negative 96. Negative 96 feet per second. So there you go. So there's a problem. It just shows you all the different things you can do with derivatives, okay? This is just really cool, I think. Just how easily knowing calculus can allow you to solve this sort of a problem. Sometimes when students take physics, I've heard them say, can I take the physics course that doesn't require calculus? They might know calculus, but they think it's going to be easier to take the physics course that doesn't require it. And I say it's kind of like saying, will you let me build a house without using power tools? Calculus is like a bunch of power tools. It just has all sorts of power and potential, and now you can use it to solve some interesting problems. Let's try one more. Suppose you have something that's moving along the line, and the position of this thing moving along the line, say this is, I'll say 0 is right here, there's 0. And let's say that the position of this thing along the line is given by t cubed minus 9t squared plus 15t plus 7. Okay? So that gives the position along the line. So right away you can see that the position at time 0 is equal to 7. So it's starting off right there at 7. That's at time 0. I'll put time equal to 0 up above, and I'll indicate the position down below. Okay? And suppose, let's just play with it again. Let's find the velocity. So the velocity is the rate of change of the position, so that's going to be 3t squared minus 18t plus 15. And I'm just going to, right away, I'm just going to take this and start playing with it because I know what I'm going to want to do with it later on. I'm going to factor this. If I factor the 3 out, I'm going to be left with t squared minus 6t plus 5, which then can also factor into t minus 5, t minus 1. That all multiplies out to that. So there's your velocity. And if you want the acceleration, let's do that as well. That's the derivative of this, which would be what? 6t minus 18. Which, of course, if you want to, you can factor 6 times t minus 3. Okay? So here's a couple questions for you. How far does the object move in the first 6 seconds? How far does the object move? How far does it travel? What's the total distance that it travels in the first 6 seconds? Well, let me clarify what I mean by that. If this object started here at time equal to 0 and at time equal to 6 it were right there, then one way of interpreting this is that this is how far it moved in the first 6 seconds. But I can't think of a better way to ask the question. But what I mean is, suppose the object did this. Suppose it did this and then it came back this way. So then it really moved. The distance that it moved was all this together with all this, and it ended up right there. So we want the total distance that it moved, not just the change of position. Okay? How far does it actually move in those first 6 seconds? Okay? So let's look at the velocity again. Let's graph the velocity. We're going to do a lot more with graphing later on in this course, but for now at least we can say this. At time equal to 1 and at 5, notice that the velocity will be 0. Here at 1 and here at 5. This is the velocity graph, right? This is time and this is the velocity. So at time equal to 1 and 5, it's equal to 0. If you put in a number greater than 5, the velocity is positive. So whatever it looks like, it's going to be going up like this. If you put in a number between 1 and 5, this, let's see, like 3, this will be 3 minus 1 is positive, 3 minus 5 is negative. Positive times negative is negative. So between 1 and 5, this thing is going to be negative. And if you put in a number to the left of 1, we're starting at 0, but say at 1/2, then what? If you put in 1/2, this is going to be negative, this is going to be negative. Negative times negative is positive, so it's going to be positive again. This thing actually, if you graphed it carefully, this would actually be a parabola. It goes down like this, bottoms out, and then comes back up. So that's the graph of v of t right there. So notice what's happening. From 0 to 1, the velocity is positive. If the velocity is positive, that means that p of t is increasing. P of t is going to the right, because if the velocity is positive, let's think about a function. If the derivative is positive, that means that the function is increasing, whereas if the derivative is negative, that means that the function is decreasing. So from 0 to 1, the velocity is positive, which means p of t will be increasing. So from this point on, p of t is going to be increasing until it gets to 1. Here you are at t is equal to 1. Let's find out what the position is there. What's the position at time equal to 1? We can stick it in there easily enough. P of 1 is equal to what? 1 minus 9 plus 15 plus 7, which is 23 minus 9, which is 14. So you end up at the point 14 here. Okay? Now what? From 1 to 5, the velocity is negative. If the velocity is negative, that means that the position is decreasing. If the velocity is negative, that means the position is decreasing, which means you're moving off to the left. So let's see once what happens by the time we get to 5. We're going to be learning more about this in coming chapters. So this is kind of an introduction to what's coming up. So by the time you get to 5, I've actually figured it out. P of 5 is equal to negative 18. Negative 18, I saved myself a little time. Negative 18. So you've done this, and now you've gone all the way down here. And here you are at negative 18, and this is when t is equal to 5. And now, what do we say for the first 6 seconds? So now once you pass 5, notice the velocity is positive again. If the velocity is positive, that means you're moving to the right. So P of 6 is equal to negative 11. So by the time you get to T of 6, you're back there again, negative 11. So what's the total distance that the object went in those first 6 seconds? Well, from here to here was 7, so total distance is going to be from here to here is 7, and then from 14 to negative 18 is a 32. You went 32 units to the left from there to there, and then it looks like you went another 7 units right here, plus 7, which is 14 and 32 is 46. So 46 feet, if the units are in feet, that would be the total distance. Okay, so there you go. I want to answer one other question here, just to show you how all this works. Question: when is the object speeding up? That is, when is the speed increasing? Okay? And the reason I ask this question is to differentiate between the velocity and the speed. If you have something that's moving 7 miles an hour this way, the speed would be 7. If something is moving 7 miles an hour this way, so it'd be, the velocity would be negative 7, the speed would still be 7. Speed basically is the absolute value of the velocity. It's always a positive quantity. Doesn't matter what direction you're going, you just want the speed rather than the direction. And so here we're interested in just the speed. So how can we get the speed? Here's v of t right there. Remember what we did way back? If you have v of t, what does the absolute value of v of t look like? Okay, the speed, call that a little bit better, is the absolute value of the velocity. And well, remember what we did? If you take the absolute value of this, anything that's positive stays positive, anything that's negative becomes positive, and then again this is positive. So there's your speed function right there. So when is it speeding up? When is the speed increasing? Well, notice that the speed is increasing. This was the point 3 right there. So the speed is increasing from 1 to 3. So t, this means is a member of the interval from 1 to 3. It belongs to the interval 1 to 3. Or the other option is once you pass 5, from 5 all the way out to infinity. So there's where the speed's increasing, right from there to there, and from there to there. And I guess I could have mentioned earlier that we know that this thing levels off here at 3 because look at the derivative of the velocity. Here's the derivative of the velocity right here. There's the acceleration. If I ask where is the acceleration equal to 0, that's at time equal to 3. So this is the graph of the velocity right there. This is a spot right here where the velocity hits a minimum, and it hits the minimum at a place where the slope is 0. So where will the slope of the velocity be 0? Here's the velocity. Where will the slope be 0? Well, I need to take the derivative of the velocity, there it is right there, and find out where the derivative of the velocity is equal to 0. So when I set the derivative of the velocity equal to 0, there it is at t equal to 3. And again, we're going to be getting into this a whole lot more later on, but this gives you kind of a nice preview of what's coming up when we do some graphing. So that's good. There we go.